Professor Lakshmi Ravishankar, and in this module, we'll be discussing the stereochemical outcome of electrocyclic reactions. So, at the end of this module, the student should be able to predict the stereochemical outcome of a ring closing of a polyene system or a ring opening of a cyclic polyene system, and also identify whether the ring closing or opening would occur under thermal or photochemical conditions, depending on what is the stereochemistry of the given product. A quick recap of what we had done in the previous modules. So in the previous module, we discussed the Foucault frontier molecular orbital theory for electrocyclic reactions. We also saw how to identify the HOMO, determine the symmetry of the HOMO with respect to the mirror plane and the C2 axis, and what is the importance of HOMO, and also the two modes of cyclization of polyenes, the con-rotatory and the disrotatory modes of cyclization. Let us revisit this 3,4-dimethyl cyclobutene derivative, which we saw in the previous module. This is the cis isomer, this is the trans isomer. If I take the cis isomer and do the reaction under thermal conditions, it ring opens up and you get the 2E4Z24-hexadiene. The same reaction under photochemical conditions gives me the diastereomer 2E4E24-hexadiene. If you were to start with the trans geometry, the 3,4-dimethyl cyclobutane, on heating it gives me 2E4E24-hexadiene, which was obtained by irradiation of the cis, and under photochemical conditions you get the diastereomer 2E4Z24-hexadiene. So let us see and try to analyze why we are getting this different stereochemical outcomes under different conditions. So 2E4E24-hexadiene is a 4-pi electron system. So there are 4 molecular orbitals and Psi2 is going to be my HOMO. So if I have to bring about a constructive overlap, now the terminal lobes are having the like sign on the opposite side. So this will have to undergo a con-rotatory closure, and if that happens, if I rotate it in this clockwise direction, both the lobes in the clockwise, there is going to be a constructive overlap, but this methyl would go up, this methyl would come down, and you would end up with the trans isomer. You could as well have done the anti-clockwise rotation, in which case this methyl would have been here, this methyl would have been here, and you would still remain a trans product. However, if you do the same reaction under photochemical conditions, you may recollect that when you do it under photochemical conditions, one of the electrons from the ground state, that is in the ground state HOMO Psi2, is excited to the first excited state. So in this case, Psi3 would become my new HOMO, and if Psi3 is the new HOMO, the like signs are on the same side. So this will have to undergo a disrotatory closure because that is allowed. And if I do that, this is going, say, in the anti-clockwise direction. This lobe is moving in the clockwise direction. It could as well have been this clockwise and this anti-clockwise. In both the cases, the product is going to be a cis dimethyl cyclobutene derivative. So one can predict the stereochemical outcome. This is a simple technique wherein you can make use of your palm and the thumb to orient the substituent. So if I assume that this is one carbon, this is the other carbon, and this carbon-carbon bond has to break, if both the thumbs are oriented like this, that becomes the cis geometry. Now if I do a con rotation, in this case it is moving in an anti-clockwise direction, the ring opening would result in the substituents pointing in this direction. So if the substituent is here, then the hydrogen has to be here. So this double bond would have an E geometry and this double bond would have a Z stereo descriptor, or this would result in an EZ stereo descriptor of the terminal olefinic carbon of the polyene. If you take the trans isomer and do the same exercise, trans would be represented like this, and you're rotating both of them in the anti-clockwise direction, you would end up with the EE or ZZ, depending. Now here you are rotating it in the anti-clockwise, so this gives me an EE stereo descriptor for the terminal double bonds, but if I were to rotate it in a clockwise direction, it would give me the ZZ. So by using this simple technique, it is quite possible for students to determine what is the stereochemical outcome of the reaction. Let us see if it works for the disrotation. So the same exercise, I have my cis 3,4-dimethyl cyclobutene. Disrotation means they have to move in the opposite directions. So this would give rise to EE or ZZ depending on whether it is clockwise or anti-clockwise, and the trans would give me the EZ configuration of the substituents on the terminal olefinic carbons of the poly. Now one would imagine that every time I see a cyclobutene, it is unlikely that it would undergo ring opening, but it is not the case. Look at this molecule where you have a cyclobutene fused to a 5-membered ring, and it is a cis fusion. If it were to undergo a Corn rotation which is thermally allowed, I would end up with an EZ13-cycloheptadiene system. However, this reaction does not proceed in this direction because to have a trans double bond in a 7-membered ring is a lot of geometrical constraints involved, and hence this reaction does not take place under thermal conditions. The molecule exists as such. A disrotation would give rise to the ZZ13-cycloheptadiene, but you know that under thermal conditions, disrotation is forbidden. So while the selection rules may allow a ring opening or a ring closing, geometrical constraints may prevent it from happening. Let us extend it further to the octatriene system. So from 4N, we are going to a 4N plus 2 system. So this is 2E4Z 6E246 octatriene. On heating, it gives me the cis 5,6-dimethyl 1,3-cyclohexadiene. If you take its diastereomer, on heating it gives me the trans product. Again, we can analyze it based on the FMO theory. So this is my Psi3 is going to be my HOMO in a 6-electron system. So if Psi3 is my HOMO, the like sign lobes will be on the same side. This will undergo a disrotation, and disrotation would result in both the substituents being cis to each other. Under photochemical conditions, from Psi3, Psi4 becomes my HOMO, and in Psi4 the like signs would be on the opposite sides. This would result in a conrotation resulting in the trans isomer. You could also use the technique of using your hand to figure out whether this is indeed coming. If you consider the all cis cyclodecapentaene, where all the double bonds are cis to each other, depending on whether it is under thermal or photochemical conditions, on irradiation you get the trans 9,10 dihydronaphthalene, but by a conrotation, and on heating you end up with the cis 9,10 dihydronaphthalene via the disrotation. So it is very possible that you may be given the starting compound, you may be given the reagents, whether it is light or heat, and asked to write down the stereochemistry of the product, or you may be given these two and asked to identify what would be the reagent conditions. Let us see if we are able to extend it further to the 8-electron system. So here you are having an octatetraene system which is substituted at the terminal carbon. So this carbon, olefinic carbon, both the hydrogens are coming on the same side. So this is Z, and this would be having the E configuration. So this is an EZ system as with respect to the terminal carbons. The question is, it gives me the cis in one case and the trans in one case, and we have to identify whether A and B, which one of these two is thermal and which one of these two is under photochemical conditions. So this is an 8-electron system, 8 MO, so Psi4 is going to be my HOMO. In Psi4 you will have the like signs on the opposite side. This would undergo closure by the conrotatory. So that much is confirmed. So now I need to see whether conrotation would give me this product or will it give me this, and accordingly my A and B would be decided. So let us make use of this technique. So this is my EZ geometry of the substituents on the terminal carbon. This is my cis product. So if I were to get this to this, it will have to undergo a conrotation. If I have to convert this to this, again it would be a conrotation, which means that A is under thermal conditions, or A would be heat. If I have to convert this to the trans, so this is how the trans would be oriented, and obviously then this would have to undergo a disrotation, imply that B has to be under photochemical conditions. So this is how one would analyze, given the reactant and the product, identify what is the reagent, whether it is heat or light, or given the reactant and the reagent, identify what is the stereochemical outcome of the product. So now let us revisit the Snezarov cyclization, which is conversion of a cross-conjugated ketone in the presence of an acid to a cyclopentanone derivative. So the Lewis acid is basically used to increase the electrophilicity of this carbon. So if you look at this, now you have a 5 carbon 4 pi electron system. So this will have 5 MOs, of which Psi2 is going to be my HOMO. Psi2 HOMO means the like signs are going to be on the opposite side. This would undergo a con rotation. I would get a geometry like this when it's moving in the clockwise direction, and a geometry like this when it loses its proton. You would end up with this cyclopentanone derivative. It is possible that you can have more than one electrocyclic reaction participating. For example, this is an 8 pi electron system. Under thermal conditions, 8 pi undergoes a con rotation electrocyclic ring closing reaction to give me this octatriene derivative, cyclooctatriene derivative. Again, you have 6 pi electrons because this can undergo further ring closure to give me this fused system, but this time it is under disrotation. I leave it to the students to find out what is going to be the geometry. Is this fusion going to be cis or trans? You could also have a diphenyl ethylene molecule. On irradiation, it undergoes cyclization by a con rotation. This could be then oxidized and you end up with an aromatic product. So by using several pericyclic reactions, it is possible to do the synthesis of simple, useful molecules. Now, in the next module, we'll be also seeing clubbing of electrocyclic and Diels-Alder reaction to end up with some very useful synthetic molecules. So to summarize, depending on the stereochemistry of the starting polyene and the nature of the energy source, whether it is heat or light, the stereochemical outcome of the reaction is different, and it is possible for us to predict what would be the stereochemical outcome. Certain cyclizations may be allowed according to the selection rule, but geometrically they may not be favored. So this brings us to the end of module 2. In the next module, which is module 3, we will be discussing cycloaddition reactions. Thank you.